In this video, we'll take a look at the metacircular interpreter. Now, what is the metacircular interpreter? Well, recall a few videos back, we created a program that developed our own REPL inside of Scheme. So we created our own read eval print loop program that used the built-in eval operation in order to take in some input from the user and determine the appropriate output. Well, the metacircular interpreter, or the MCI, you can think of as an extension of that REPL program, where instead of using the built-in eval function, we've created our own process for handling that translation from inputs to outputs. So let's see what the MCI does before we try and understand how it does it. So let's just run this program real quick here. Run the program, we get a prompt here that's asking for some sort of input, and this is asking for any sort of scheme expression. So I could say something like +1, 2, and it tells me the value of that is 3. I could give it a more evolved or a more involved operation like define f of x to be plus the car of consing x to itself +7, let's say. Close all of those. And now that doesn't have any value, so it just says, okay, that worked. But if we want to get a value out of that expression, we can maybe run that function f of 3. And we get back all the work. Let me get this code up on the screen here. 3 goes into x. We cons x and x together, so we get the pair of 3.3. We take the car of that pair, so just 3 again, and then add that to 7. So it does all the same work that we'd normally do, just now we've created the program that does it for us rather than depending on the built-in scheme. So I'm going to scroll all the way to the bottom of this fairly lengthy piece of code here. There we go. Down to the driver loop here, and this is essentially the same part of the code that resembles the REPL that we've seen before. So what this does is it reads an input from the user, so it takes some sort of expression, and then it determines the output to be whatever happens when we evaluate that input inside of some global environment. Now, eval here, though, is not the built-in eval that we saw before, but rather, let's scroll all the way to the top again, a function that we can actually walk through, understand, and if we want to, modify. So the MCI is just an interpreter. It's a metacircular interpreter, but it is just an interpreter. And an interpreter is just a program. Okay, so it reads expressions of one language and attempts to assess the values of expressions in that language. Let's say to take input symbols and convert those into output symbols. Okay, so it's a program that takes in symbols and outputs different symbols. So the language here becomes an interface between two different layers of abstraction, separating the programmer from the hardware, the machine language underneath. And the interpreter then is the implementation of that interface. We can specify expressions in the language, and the interpreter can take those expressions and turn them down into machine comparable expressions to actually be computed. Okay, so all interpreters are just programs. A metacircular interpreter, however, is a little bit odd from a normal interpreter. So here we're going to be translating from Scheme into Scheme. That is to say, our interpreter does the work of translating our inputs into inputs in the same language. So metacircular just means that the interpreter is written in the same language that it evaluates. So in this case, our interpreter is written in Scheme and it interprets Scheme as well, which is handy because it ends up working with the same data structures as the underlying implementation. That is to say, we don't have to convert from trees or Java syntax into Scheme before we can determine the basic forms of combination. We're using the basic forms from Scheme in Scheme. So the underlying implementation gives those structures some meaning, which does simplify our effort here a little bit. Now, you might think, well, what's the point of that? If we already have something that can take that next step and take our Scheme instructions and bring them down to machine level instructions, why create this metacircular interpreter? Well, it's useful for two main reasons. First, as a learning tool. So by having the metacircular interpreter in front of us, we can see how the bare bones of the language are constructed. We have a specification of the language right in front of our eyes, one that we can modify and extend if we wish to as well. So it's a very good way of understanding how evaluations, bindings, environments all work together to structure a language. Now, the second reason why metacircular interpreters are used in general is that it becomes a non-trivial test case of a language. So imagine if you had just created this brand new language or a superset of some existing language, and you want to make sure that this thing is is robust. It's going to work in a lot of other situations. So creating an interpreter in that language is a very good test case. It's a consistency check that it can reproduce its own code. Okay. It also creates a system where we have high-level compiler design, which is to say we can write the compiler in this high-level language that it compiles. Right? It's easier to express the thoughts and ideas that we have in these higher level languages than it would be to write an interpreter, let's say, in machine language itself. There is an issue here, though, sort of a chicken and the egg problem, where we can't define an entire language in itself. Right? There has to be some sort of external elements from which to build the implementation. These are things like the primitive operations and the core mechanics, which are either machine instructions or from some underlying language like C, perhaps. So for example, the very first Java compiler was written in C and C++, but now Oracle's Java C is written strictly in Java. So this bootstrap, as it's called, this underlying implementation, will be Racket's implementation of Scheme as we've become familiar with it. But what we're going to do is break down input expressions as best we can into the components or primitive components that will then pass off to the underlying scheme to finally do things like addition and what have you. So the MCI is not a complete language specification. It is a bit of an abstraction of what an interpreter can and should be. It does describe how an environment model can be used in conjunction with an eval-apply loop in order to compute input expressions into output values. But it doesn't describe things like a memory management or garbage collection. All that's left to the underlying Dr. Racket's implementation. It doesn't define an editor or any sort of file interpretation. It's REPL only. And it does use, as I mentioned, the scheme's underlying evaluator to invoke primitive procedures, things like plus, minus, what have you. So the core of the MCI works by essentially implementing the eval-apply process. So we've been over the eval-apply process, what it is and how it works, but just to quickly repeat myself, eval-apply is essentially two mutual subfunctions, mutually recursive subfunctions, where eval takes in some sort of input expression, such as what would be typed by the user, and outputs the value of that expression. And it does so by first evaluating all of the sub-expressions in that input, and then applying the value of the procedure to the value of the arguments. Okay. Then the apply process, or the apply function, says given an input procedure and a list of arguments, values, combine those two things, apply that function to those arguments and output a value. And now that apply step can take two different forms depending on the nature of the input function. If we have a primitive function, we just sort of run through the steps. We sort of say that happens atomically in our substitution model, for example. In this case, we're just going to delegate all of those operations to the underlying implementation. That is, say, Racket's scheme implementation of the plus operator or the multiplication operator. So we won't break those down any further. But if we have a compound function, something like a defined function or a lambda, what happens is we need to first extend the environment. So remember, in our contour diagrams, we drew a new contour. We binded all the parameters to the values. So the arguments coming out of eval into apply. We want to bind all the parameters from our function to the argument values coming in. And then we'll call eval on the body of that procedure within a new environment. So notice, importantly, eval calls apply in order to combine functions and its arguments, and apply ultimately can call eval as well by running through, in order to run through the body of that procedure itself. So the core of the MCI is these two mutually recursive procedures. And let's actually just walk through the code of them. So if you want, you can go through the text notes here, and if you notice, if you mouse over any of the functions, it has little handy tooltips that helps you sort of keep track of where everything is, and it's pretty well organized and has lots of detailed notes. But what I'm going to do for most of this lecture is actually just walk through the code itself. So here's the eval function right up at the top. And what eval does, as I mentioned, is its purpose is to determine the value of some expression. So you can see the arguments to the eval function are some expression and some environment. And we've seen down at the bottom here, when eval is first called by the driver loop, here it is, we call eval with some expression, which is just whatever the user typed, and some environment. We'll talk about how the environment works in a subsequent video in this chapter. But for now, let's just talk about how to actually process these expressions. Okay, so back to eval, way at the top again. So eval takes in some expression and some environment in which provides the context for evaluating. So if we have some variables, environments where we're going to find the values associated with those variables. Now, the body of eval is broken down into two main parts, where the first part is essentially a switchboard of special forms, and the second part is the default application of just sort of generic functions. So the special forms, they come in a variety of different types. So we have variables and quotes, or the assignment operations, or if statements and lambdas. And essentially what this does is it says, is this expression of the form of an if statement? If so, then we need to apply some special rules of evaluation, right? The whole thing about special forms is that they're not treated like regular function application. So if we have one of these special forms, then we have to have some sort of special rules of evaluating those. Okay? It's also worth pointing out that self-evaluating expressions are here. This is things like numbers and strings. Those, we just return the expression themselves. So you can consider those as a kind of special form as well, if you would like. Now, the second part, as I mentioned, is the sort of default case or application for non-special forms. So in that case, we have some sort of expression. It's well-formed, it's syntactically valid, but it's not one of these special forms, so we're just going to use the regular rules. The regular rules for eval say, evaluate the sub-expressions and apply the argument. So that's what this does here. And we'll come back to that, but let's walk through some of these piece by piece. So these special forms, again, the idea of how we're structuring the eval process is first we need to determine, is this thing a special form? And if so, we'll have some special rules for handling that form. So we have a way of determining, is this thing an if statement? And if so, we'll then evaluate that thing as an if statement. Okay? Is this thing a lambda? If so, then we'll make a procedure out of the different parts and we'll evaluate that lambda. Is this thing a begin statement? Then we'll evaluate a sequence of actions and return the value of the last one. So notice there's a bit of an abstraction barrier inside this eval function. It separates concepts like if statements from their syntactic implementation, right? We have a way of saying, is this an if statement? If so, eval it like an if statement. Nowhere in there does it specify what an if statement looks like or how to evaluate them. The eval is just sort of separating out the different pathways of evaluating the various types of expressions. So this abstraction barrier is made up of a bunch of predicates. We have ways of determining the different functions, some accessors, so things like functions for grabbing the parameter section out of a lambda expression, or for grabbing the body section out of a lambda expression, and even constructors, so making a new procedure out of all of those things. There's in fact more accessors and procedures below this layer, but for now just assume that this abstraction barrier works, and we'll move down the layers in subsequent steps of understanding this MCI. Okay, so for now the takeaway is eval organizes and breaks down, that is to say decomposes, the various expression parts into more meaningful sub-expressions. Okay, and then it will eventually use apply to get those to get the value of those combinations if necessary. So the apply step, if we don't have a special form, it ends up down here. An application here, this predicate for determining is the expression and application, essentially is true if it's a syntactically valid combination. So if it's essentially a list where the head of that list isn't one of these special forms, then we'll assume it's a function and we'll attempt to apply it. Now, the apply step says call the apply function with some arguments. So the apply functions down here, we'll come to that in just a second, but what are these arguments? So as I mentioned before, the steps of the eval process in a standard applicative order evaluation say evaluate the sub-expressions and then apply the value of the function to the value of its arguments. Okay, so this first argument to apply first determines the value of the first part of a combination. So operator here is an accessor that takes the first element out of an expression and evaluates it. So if that operator, if the first element of this expression is, let's say, the symbol f, then eval will eventually determine that's a variable and will return the value of that variable, which should be some sort of procedure object. Okay, so that's the first argument to apply. It says determine what the first value in that combination is, which should be a procedure object. And the second step says essentially the same sort of thing, evaluate the other sub-expressions, but in this case give back a list of all of their values. Okay, so the operands here is again a selector for taking everything else out of a combination. So if I said something like F123, operator returns the first part, so the F, and operands essentially is just CDR, it takes everything else. So it gets the list of expressions, which might not be simple arguments, right? We could have F of 1 and then 1 plus 1, and then, I don't know, 3 times 2, something like that. So these combinations need to be evaluated before we can pass them into apply. We need to know that this is 2, not just some combination. So list of values essentially maps the eval function across all of these arguments. So what this does is it will return a list of all of the values associated with these expressions. So the list 1, 2, and 6 in the case that I've typed here. Okay. And now that's the second argument to apply. So the first one is the procedure object, the evaluated procedure object, not just the symbol representing it. And the second one is the list of all the values of the arguments for that procedure object. We pass both of those into the apply function, and then apply takes it from there. So the apply procedure takes a procedure object and a list of arguments as its arguments. And the objective of apply is to invoke that procedure on that list of arguments. So a procedure in the MCI looks a little bit different than what we've seen. So something along the lines here, I can actually show you. If I say lambda x, just square something, times xx, the value of that should be a procedure object, right? This is essentially create a procedure, and this is what a procedure object looks like underneath in this MCI. So compound procedure has a list of parameters, a list of expressions that make up the body of that procedure, and then some sort of environment. And this is actually pretty printed. This is sort of a placeholder for the actual environment, which is essentially a long list of bindings. Again, we'll talk about environments in the future. But the idea here is, let's write this down here. Procedures look something like this. Compound procedure. Then we have some sort of param list, some sort of body list, so I guess just body, and then some sort of environment. Okay, so it's a combination of 4 things. The label that it is a compound procedure, and then all of the information relevant to invoking that procedure. Now, when we're using the apply procedure, the apply process here, it breaks the idea of applying into 2 steps. Where the first step, or sorry, 2 potential branches. Where the first branch is for all the applications of primitive procedures, so things like plus, cons, and other arithmetic operations. For all of these, we're just going to let the underlying scheme implementation just evaluate that function right away. All of these arguments are already at their simplest values, and this procedure is just an object, so if it's a primitive procedure object, then it just says apply that primitive procedure right away to the different arguments. In fact, let me just show you what that looks like. This actually uses the underlying scheme's implementation, so you can say something like apply the plus procedure to the list 321, for example. Okay, that just says take this procedure object and apply it to these arguments. Okay, and that's what our apply will do as well, just we're implementing it ourselves. So if it has a primitive operation, then that's just done right away in a single step. But if we have a compound procedure, so things like squaring or lambdas or all this other stuff that we can define, this has to be done in 2 steps. The first step is to extend the environment, and the second step is to evaluate the body in this new environment. So let's take a look at this. If we have some sort of compound procedure, so that's a procedure that starts with the words compound procedure essentially, then what we need to do is evaluate the body of that procedure in a new environment. So we're going to call eval, specifically eval sequence, because there could be more than one expression in a procedure body, right? We could have had lambda display hello and then times xx. So eval sequence just evaluates each element of the, each expression in the body of the procedure, and then returns the value of the last expression. Okay. So what it is in fact evaluating is the procedure body. So this is an accessor through that abstraction barrier. So if the procedure object looks like this, then procedure body here is just going to return whatever is in this part. So the list of expressions that make up the procedure. So for us, that would be the list that contains one element, where that element is a single expression times xx. Okay, so we want to evaluate all of those, but we want to do so in an environment where those parameters now have values. So to do that, we need to extend the environment. And again, we'll talk about how this actually works, but let's take a quick look at what's happening here. And then we'll learn about the how a little bit later on. So extend environment needs to essentially take in an existing environment and attach the new local scope onto that. So the existing environment for our lambda here, if we were to run it, would be the global scope and the primitive scope. So all the bindings for things like multiplication, times, and all those. And we've also defined a function f here that has the value of whatever lambda we've constructed it to. So the existing environment, which was this procedure environment here, so the thing that is held in the procedure. So recall when we define a procedure just in scheme anywhere outside of the MCI as well as inside, what we create is a closure, which contains, as I've been describing it, 2 pointers. A pointer to the procedure's text, so to the lambda itself, and a pointer to the parent or the referencing environment. So that's what's happening in this compound procedure. Instead of having 2 pointers, we just have 3 lists, but it's the same idea. So we have this first part would correspond to what I've been calling the first pointer. So it's the list of all the params and all of the expressions in the body of that procedure. And the second part here would be the environment. That's a reference to the enclosing scope, essentially. So if we want to be able to extend the context of the function, we need to extend the context of the lexically enclosing block. So that would be this piece of information stored with the procedure itself. So that's what this line does. It says access this part of the expression, so get the existing environment, and then extend that environment by creating a new frame of binding. So all the procedure parameters, so that's essentially an accessor for this, get unified with, sorry, not unified, get associated with all of the different arguments. So that's the input here. So this parameters would be the list x in our case that we saw here. And if we called this function with, let's say, the value 3, that 3 would be inside these arguments. So we're going to extend the environment by creating an association between all of the parameters and all of the arguments, so binding 1-to-1 for each one. And we're going to attach that onto the front of the existing environment, so the procedure's already existing context. Okay, so we'll see later how all of this works, but for now, just understand that we need to extend the existing environment by creating a new frame. So we've seen how this works in the contour model, for example. We draw a new box. Inside that box, we put a new frame. That's exactly what this is doing. It's creating that new contour inside our model, and then we go to evaluate the body of that procedure inside that new contour. All right, so let's actually see some of this. I think it'll be a bit more informative than listening to me talk through a video. So what I'm going to do is add in some display statements here so we can actually see the different steps as they're occurring. So display eval, and we're going to just display the different expressions as they show up. And we'll also put in an apply here. So display apply. And in this case, I'm not just going to use a regular display. I'll show you why later on, but I'm going to use what's called user print, which is a function built in later on inside the MCI that lets us pretty print procedures. So the argument procedure here, we're going to use the user print, and that essentially gives us this output, which the main difference between that and display is that the user print hides what's actually in the environment, because again, it's this massive list of all sorts of bindings all the way up to the primitive scope, which is quite messy if you display it every time, so we're going to just hide that behind a placeholder. All right, so user print procedure, and a bit of a separator here, spaces, and display the arguments as well. Okay. So with those in mind, let's rerun our code here and just try evaluating a few things. So let's go up to eval and ask, what is the value of 3? So we call this, so recall all of that information is going into the main loop here. So whatever we're typing in is our input, and then that goes directly into eval. So all the steps we see down here, they start here, and then essentially we'll see a mutually recursive process when it's needed. So if we pass in a 3, though, that comes into eval. We display that we're evaluating a 3, and that ends up being self-evaluating. Integers, strings, constants, essentially, they don't change, and they don't have any hidden value. So we just return the value as it was passed in. A 3 is a 3 is a 3. Okay. Let's do a slightly more involved one here. If hashtag t, oh, it's actually true in the MCI, plus 5, 2, and minus 5, 1. So somewhere down at the bottom where we define the primitive environment, the hashtag T for true, which is native in Scheme, is changed in this environment to be the word true, like in Java or in Python, for example. So let's evaluate this. And we get a few more steps here. So here's what I typed. So that went straight into the eval process as the entire expression. But then the job of the entire expression is to evaluate different parts of that. So in this case, it goes through all these steps and says, is this thing an if expression? Now, because this is an if expression, we already know what rules should be followed, right? If is a special form that says evaluate the condition. If it's true or false, then evaluate one of the two branches, but never both. So if we look at what gets evaluated, it evaluates the entire thing. Then it evaluates the condition, which was just true, so that's pretty easy. And then it evaluates one of the branches. So if it's true, it should be evaluating this branch, and that is in fact the branch that it's evaluating. But in order to determine the value of that whole combination, it has to break down the sub-expressions. So this case, if we passed in this combination to eval, it doesn't land in any of these special forms, right? It's not a quote, it's not an assignment, it's not an if statement, blah, 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 all the way down to application. So at that point, it's a well-formed combination that's not any of these other special forms, so we're going to try to apply the function. So in order to do that, we have to first evaluate all of the sub-expressions. So we have to figure out what is the value of the operator, and so we can see called eval on the operator. We have to figure out what is the value of each of the different operands as well. So we can see a called eval on 5 and a called eval on 2, both of which would be self-evaluating. Now the operator here is a plus, which is a symbol, so a variable name. So that would come down to this variable line here, which again, we'll see how the variables get looked up in an environment in one of the subsequent videos. But as we can see, it found the value for all three of these things and then said apply the value of procedure to the arguments listed. So that's this line here saying all of that. So it displays the primitive procedure, which looks a little bit different than compound procedures. Primitive procedure, which is just essentially a link to the underlying Scheme implementation. Remember, that's what happens if we type in what is the value of plus in a normal Scheme window. And we're applying that to the values 5 and 2. And because that's a primitive procedure, it's done essentially instantly. Actually, I'll show you where this is. Just jump to the definition. So apply primitive procedure says call apply an underlying Scheme. Now that... all the way back to the top again. Apply an underlying Scheme is in fact just an alias for the default apply. We had to do this at the top because we redefined what apply was. So before we lost what that used to be, we just gave it a different name, and then we used apply as our own version and apply an underlying Scheme as the original version. So when we call apply with a primitive procedure in the values 5 and 2, it gets to this line, and that essentially just says combine them as you normally would, add 5 to 2, and we get 7. Okay. Let's do another layer here. I think this one should be pretty self-explanatory based on what we've covered already. But another combination now with a bunch of steps. So let's just see what this does to our Scheme. Oof. Scroll up, please. There we go. Okay, so I passed in this arithmetic combination and says eval that whole thing. And now we've seen the process of eval-apply going way back to, I think, chapter 2 or 3 when we first started doing Scheme. We walked through all the different eval-apply steps. And in fact, if you wanted to do this on paper, you'd end up with the same steps that we see here. So we evaluate the entire expression. In order to do that, we have to evaluate the 3 sub-expressions, so 1, 2, and 3. So we get plus, which is just the symbol for addition. We get times 2, 3, which is a combination, so we have to evaluate those sub-expressions times 2 and 3. And then finally, we can apply that to get its value. So that should give us back 6. We didn't output any of the results here, so we're just getting the inputs, but we can assert that times 2, 3 should be 6. So that's the second combination from the input. And then the third combination times 4, 5. Again, break down the sub-expressions and then apply them to get the whole answer. And now we have plus 6 and 20. So then we can finally apply all of those at the top level. So we have mutually recursive processes that essentially build up all of this these step-by-step operations in order to take our input expressions and give us back some meaningful values. Okay. Let's do one with a function this time. So let's say, let's define a function square x as times xx. So in the eval steps for this, notice there was no apply line. So it said eval the original expression, which goes to, I guess that'd be definition. And then eval definition has its own special rules. It says, okay, well, in this case, we're creating a lambda. So what that does is it ends up constructing the lambda and saying evaluate that lambda, and then associating it with some name. We'll talk about the special eval rules later on, but for now you can see that it evaluated the original expression, and then in order to determine, or in order to follow through on that expression, we have to create a function and bind it to the name square. So the next line it said, well, we're creating that function, we want to get that function object back, so there's that eval as well, and then presumably inside eval definition, that unification, or sorry, that binding happens between square and this lambda. Now notice there's no apply step here because we're not actually invoking that function, but if we wanted to do that, we can do that as well. Something like sqr plus 1, 2. And if we run this, much bigger expression. So evaluate the entire thing. In order to get that value, we have to get the values of the sub-expression, so square and plus 1, 2. In order to get this, we have to evaluate its sub-expression, so plus 1 and 2, and then finally applying those together to get 3. Now we have the procedure for squaring and the number 3, so we're going to apply this compound procedure to the list of arguments, which is just 3. Now, in order to do that apply, let's go down to our apply step here. It says extend the environment, which we're not going to see in our output here, but presumably we now have that extra contour drawn in our diagram, if you want to call it that. And then it says eval sequence, so evaluate all of the expressions in the procedure body, which we can see is essentially just times xx, but do so in this newly extended environment, where x has the value 3. Okay, so it says evaluate times xx, so evaluate times, we figure out that's the procedure for multiplication. We evaluate x, we find that's a variable that happens to be bound to 3 because we just made that extension into our environment. And again, we evaluate x a second time and get 3 there as well. Now, since this is still a combination, we have the procedure for multiplication and the argument list 3 and 3. We apply that procedure to that argument list in order to do the actual arithmetic step. It comes back to apply a second time as a primitive procedure and does that multiplication. Okay, so the eval-apply loop are the core recursive definition of the metacircular interpreter. They break the code down, build up an environment, and determine the results of the expressions that we type in. I think that's good for one video. It's a solid introduction to the MCI. In the next video, we'll break through this abstraction barrier to see how eval and apply can do all of these things without just sort of hand-waving and saying, well, there's a predicate that lets us know that it's an if statement and an evaluator that lets us determine the value of that if statement. So we'll go through and see what's on the other side of this abstraction barrier, and we'll see how pretty much all of this is done just by manipulating lists.